Hi everybody, welcome back to the channel. In this video we're going to take a look at continuity and what it means for a function to be continuous. And every calculus book actually kind of starts out the same way, or at least every one that I've seen. Every Calculus 1 book starts out by talking about limits, and that's because you need limits in order to talk about continuity. And once you talk about continuity, then you can talk about another topic that's going to be coming up in the near future for us, which is something I actually mentioned in a past video, something about an idea called the derivative. And so you need limits to talk about continuity. You need continuity to talk about a derivative. And so we're kind of building up this foundation of important concepts in calculus. And so you've heard of the idea of continuity before. You probably have. And that's what we're going to look at in here. So continuity. And first we're going to start out by looking at what does it mean for a function to be continuous at a specific point. We'll also look at kind of within that, what does it mean for a function to be discontinuous or not continuous? And then what are some common functions that we could take a look at, and what can we tell about where they are continuous or where they're not continuous? So that's kind of the goal of this video, and within that we'll look at some examples as well. So first of all, let's talk about what it means to be continuous at a specific point. So we're going to put it this way. Let's say f is continuous. This is really like a definition. This is something to go back to and just make sure that if we're going to say that a function is continuous at a point, that it satisfies a certain definition, certain criteria. So f is continuous at a point. We'll just call that point A. So we'll say f is continuous at a point A if the limit as x approaches A of f of x, we need that to be equal to f of A. Okay, and that might not seem too crazy, but think back to the last couple videos that we looked at when we talked about limits. We had this idea that in order for the limit here to exist as x goes to A, notice this is a general limit. There's no little negative sign or little positive sign. This is not talking about a limit from the left or a limit from the right. This is a general limit. In order for that limit to exist, this also means that the limit as x goes to A from the left is equal to the limit as x goes to A from the right. So both the left-hand limit and the right-hand limit need to be equal, and they both need to be equal to whatever f of A is. So this is a point, and basically what this means is that you can't really have any holes, and then the fact that you have the left-hand limit and the right-hand limit being equal means you're not allowed to kind of have any jumps or kind of think about breaks or gaps in your graph. Really, an informal way to think about continuity is this. Could you draw your graph without picking up your pencil? Okay, could you draw the whole thing all at once? If somehow when you're drawing your graph you are forced to pick up your pencil, either because there's a break in the graph or because there's a hole in the graph somewhere, then wherever you had to pick up your pencil, whatever that x value is, the function would not be continuous there. Let's look at a graph here. Let's suppose that you have a graph that looks like this, except in one spot you have a little hole. And so clearly we could think about kind of what piece of the definition is not satisfied, because what we just said is that really at this point, whatever this is, maybe this is x equals 2, we just said that the function is not continuous at 2. So which of the criteria is not met, or what part of the definition doesn't hold if f of x is not continuous here at 2? So in this example where you have a hole, we would not have f of a. Maybe f of a is not defined, or maybe f of a is like up here somewhere, where f of a gives you a different value than the left-hand limit and the right-hand limit. So if you have a hole, that's what that would look like. If we have another graph where we could have something, let me kind of make this like a piecewise function over here, where you might have something that looks like this, and you kind of have two pieces, and you have this break or this gap right here in your graph, and so obviously then here the right hand limit and the left hand limit are not equal. So even though there's a closed circle point up here where f of a is defined, the left hand limit and the right hand limit are not equal. So we need the left and right hand limits to be equal, and we need those to both be equal to whatever f of a is. That's the definition of what does it mean to be for a function to be continuous at a specific point. Now let's take a look at an example. Let's say we have the function that looks like f of x equals x minus 1 over x squared minus 1. This is actually a function that we saw back a couple of videos ago when we talked about limits. And we could ask a question like, for what values of x is f discontinuous, and on what intervals is f continuous? I might even throw in kind of a second part to that first question. For what values of x is f discontinuous? And I might even kind of throw in a follow-up question of what part of the definition breaks down. So what part of the definition does not apply? Okay. What part of the definition does not hold? That's how I'll say it. So is it that f of a doesn't exist, or is it that the left-hand limit and the right-hand limit are not equal? What is the issue that's causing a discontinuity? That's something we can think about. Okay, so we can go ahead and look at the domain of this function. That would be a good place to start. And the domain of this function, again, something you should have seen a lot of in a past class, is all real numbers except x is not allowed to be 1 or negative 1, okay, except x equals 1 or negative 1. And so we have discontinuities at 1 and negative 1, and so the question is, what kind of discontinuities are they? This is a rational function. Do we have holes? Do we have vertical asymptotes? What do those look like? Okay, so let's say we have f of x equals x minus 1 over x squared minus 1. We can go ahead and factor the bottom. We get x minus 1 over x plus 1, x minus 1, and you have an x minus 1 that cancels on top and on bottom. You probably remember from past class that when you have something that cancels on top and bottom, that means that you have a hole there. So for x minus 1, when you set that equal to 0 and you get x equals positive 1, there's a hole there. Okay, so there's still a discontinuity there, but again, we want to think about what kind of a discontinuity or what's causing that discontinuity. So the hole there means f of a or f of 1 does not exist. Okay, and then there's still also a discontinuity at x equals negative 1. But you may remember from past class that that's not a hole, that's actually a vertical asymptote. Okay, and so this this graph is going to look something like this, where like at 1 we have a hole, and at negative 1 we have a vertical asymptote. So negative 1, there's kind of your vertical asymptote. You're going to have something like this. I guess it doesn't go quite that low. It kind of goes right here, something like that, and kind of levels out. There's actually a horizontal asymptote here as well. Okay, and we'll talk about horizontal asymptotes actually in the next section. But there's a hole, even though it doesn't show up on my graph right now, there's a hole at 1, right about there. Okay, so that's supposed to be a hole there. So when for x equals negative 1, there's a vertical asymptote there. The part of the definition there that breaks down is that the limit as x goes to negative 1 from the left of f of x is not equal to the limit as x goes to -1 from the right of f of x. So there's not a whole, but the left and the right-hand limits are not equal. Okay. So we still have to answer the last question. Remember, the last question was, on what intervals is this function continuous? So this function is continuous on the intervals from -infinity up to -1, union -1 up to 1, union 1 up to infinity. In fact, those are the same intervals for if we had the question of what is the domain of this function, we'd have exactly the same answer. In fact, this is going to be a common occurrence, is that we have a function that the phrase we're going to use is continuous on its domain. So wherever the function is defined, that's also where it's continuous. That's not true for every function, but that is true for a lot of functions. And so we'll kind of look at a list of what functions have that criteria where they are continuous on their domain. Now, before we look at some examples, I want to look at just a couple of other properties about continuity. And when we talked about limits, we had the idea of a general limit, and then we also talked about the idea of a limit from the left and a limit from the right. So you might ask a question like, hey, do we have something like that with continuity? Because the definition of a limit is a part of the definition of continuity anyways. So does that same idea or something like that still apply for continuity? And the answer is actually yes. We can talk about a function being continuous from the left, and this is not as commonly used, but it's still just a good thing to think about, or f being continuous from the right, and it's almost exactly the same thing as the definition of just general continuity, okay? So if we think about what does it mean for f to be continuous from the left, what it means is that the limit as x goes to a from the left of f of x equals f of a. You don't necessarily need the general limit to be equal to f of a, because we're not necessarily talking about being continuous in general, we're just talking about being continuous from the left. And same thing down here is when we're talking about being continuous from the right, all we need is that the limit as x goes to a from the right of f of x is equal to f of a. So this is really more applicable when the function is not continuous at a point, especially when we're talking about piecewise functions. And when you're thinking about the left-hand limit and the right-hand limit not being equal, we could still ask a question like, is a function continuous from the left or is a function continuous from the right?